students, welcome back. In this video we are going to discuss about the variation of acceleration due to gravity of the earth, and also we are going to discuss about the Kepler's law, what are the laws of Kepler's and what are the governing formulas of the Kepler's law. So let's get started. Hello students, we have already studied gravitational field and gravitational potential at various points due to various shapes. Now we are going to study variation in acceleration due to gravity of earth. The variation in acceleration due to gravity of earth may vary due to height from the surface, due to rotation of the earth. So there are many cases we are going to study one by one. Now we are going to start case 1, variation due to height from the surface. Now let us consider a earth of radius r and mass m. O denotes the center of the earth, P denotes the surface of the earth, and Q denotes the height h from the surface of the earth. So the distance from the center of object at Q is r plus h. Now we know that from Newton's second law, F is equal to mass into acceleration, and here acceleration due to gravity of earth is denoted by g instead of a. So F is equal to mg. So now g is equal to F by m. So acceleration due to gravity, g is equal to F by m. Now find the force between earth and the object, and where distance between the center of the earth and the object is r plus h. In that case, F is equal to g capital M mass of earth and small m mass of object divided by the distance between the earth, center of the earth and the object, that is r plus h whole square. Okay, so this is the force acting between the object and the center of the earth. This is attractive in nature. Now we are going to divide this from the mass of the object, so we can find the acceleration due to gravity of the earth. So g is equal to F by m. This is the F value, so we will divide by small m. So g is equal to gm by r plus h whole square. Now we can take common r, so it will give gm divided by r square, bracket here r taken as common, so here 1 and here h by r, okay, whole square. Since g naught is equal to gm by r square is g at surface, now we can put h is equal to 0 here, h is equal to 0. If we want to find acceleration due to gravity on the surface of the earth, here h is equal to 0. So put here h is equal to 0 to find acceleration due to gravity of the earth at the surface. So g naught is equal to gm by r square. Now this is the special case, acceleration due to gravity of the earth on the surface, gm by r square. But acceleration due to gravity of earth at particular height h from the surface of earth is given by g is equal to gm by r square into 1 plus h by r whole square. Gm by r square can be written as g naught, that is g at surface. So g at height h is equal to g naught, that is g at surface, divided by 1 plus h by r whole square. This is the general formula for g at height h from the surface of the earth. Now if h is much smaller than r, then h is much smaller than r. In that case G above is equal to G naught into 1 plus h by r power minus 2. So it can be approximated as G naught into 1 minus 2h by r. So G above is equal can be approximated as G naught into 1 minus 2h by r. The conclusion from the above equation is the value of G decreases as one goes up. The meaning is when you goes up from the surface, the acceleration due to gravity of earth will decrease. Okay. Now, if h is inside the earth, okay, if h is inside the earth, in that case F is equal to Gmm divided by r cube into r minus h. The r minus h, because this is the earth solid sphere and this is the r and h depth, this is the h, so we have to take this distance, so this is r minus h. Okay, so solid, so this is the gravitational intensity E inside the solid sphere. Okay, since F is equal to me, we can write gravitational intensity inside the solid sphere. Since earth is a solid sphere, then we can multiply the mass m, so this will give the gmm rq into r minus h. So G inside the earth, we have to divide this by m, so gm by rq into r minus h. So G inside the earth is equal to G naught, this can be G naught, so 1 minus h by r. The conclusion is the value of G decreases as one goes down. All these three cases can be concluded as this is the earth, this is the earth surface. The acceleration due to gravity of earth at surface is taken as z naught and gm by r square, where g is the gravitational constant, m is the mass of the earth, r is the radius of the earth. When we goes above the surface of the earth, the acceleration due to gravity of earth will decrease, and also when we go inside the surface of the earth, acceleration due to gravity of earth also decreases. That is, Gmax will be at the surface of the earth. Acceleration due to gravity of the earth will be maximum at the surface of the earth. So here these are the 3 points. Next, variation of acceleration due to gravity of earth due to rotation of the earth. So let us consider this is the earth of mass m, this is the equator and this is the pole, north pole, south pole, this is the equator. Now let us consider a mass m is on the surface of the earth. If the colatitude of the location of the particle is theta, this is the colatitude theta from the pole, so this is the distance r from the center and it is the radius of the earth, so this is the r cos theta, this length, and this is the r sin theta, so small r is equal to capital R sin theta. Okay, now F gravity, this is the F gravity, force of attraction, is equal to G into m1 m2 by r square. Okay, G m1 into r square, or gm by r square, gm by r square can be written as G, okay, or G naught. So F gravity is equal to mg. Now since we are considering here rotation of the earth, so the earth is rotating around its pole, around its axis, so we can consider this particle is also rotating in a circular motion, and centrifugal force is given by m omega square r, and here r is equal to capital R sin theta we can put here. So if centrifugal force is equal to m omega square r sin theta. Now theta is equal to 0 will give the pole, and theta is equal to pi by 2 means 90 degree will give the equator. So at equator theta is equal to pi by 2, and here at equator this is the direction of mg and this is the direction of f centrifugal. So both are in opposite direction. So net force is equal to, at equator, F equator is equal to mg, this is the mg minus F centrifugal, so mg minus m omega square r, and that is F equator. So we have to divide F to find G equator, we have to divide by mass. So G dash equator is equal to G minus omega square r. This is the most important formula, one of the most important formula. G dash equator is equal to G minus omega square r, and at pole theta is equal to 0. Thus here centrifugal force is equal to 0 and only F pole is equal to mg. So G dash pole is equal to G. So G due to rotation is minimum at equator due to opposite direction. The G acceleration due to gravity of Earth is minimum at equator and maximum at poles. So keep in mind there are two cases. G is maximum at surface. If we are considering in height, then G is maximum at on its surface. G is decreasing above the surface, G is decreasing below the surface, that is G is maximum on the surface. And if we are considering rotation of the earth, then G is minimum at its equator and G is maximum at its poles because of its centrifugal force. And G dash equator is equal to G minus omega square r, where omega is the rotation of the earth, rotational velocity, angular velocity, and r is the radius of the earth, and G dash pole is equal to G. Okay, now go ahead. Question 1. Find the acceleration due to gravity. Find the acceleration due to gravity of the moon at a point 1000 km above the moon surface. Mass of moon is this and its radius is this. So let us consider this is the moon. Okay, this is the moon. This is the radius. Radius is, this is the radius. This is the radius. Mass of moon is mass of moon, and this is the h. Okay, so now we have to find the acceleration due to gravity. So G is equal to, we have to find G. So G is equal to capital G. Here is the any mass and this is the height. H is equal to 1000 km. So G, mass of moon, G m1 m2 is divided, and r plus h whole square. Okay, it can also be written as F is equal to, just write the force. So F is equal to G m1 moon into m1 m2 by r plus h whole square. Now G is equal to F by m. So we can write, this will give G m moon by r plus h whole square. Okay, both are the same. Now we can put, this is the method 1 This is the method 2. Okay, now we can put g is equal to g, the value of g is 6.7 into 10 to the power minus 11, value of m is 7.4 into 10 to the power 22. Okay, we are putting these values in SI unit. R is how much? Radius is 1740 kilometer and h is also in kilometers, so 1000. Okay, this is into 10 to the power 3, so this will give in meter. Now this we have to square it, so this is the square. Calculate this value, this will give meter per second square. This is the accretion due to gravity of the moon. Okay, just find it, calculate it. Now next question. Next, Kepler's law. Kepler given there 3 laws. First law is law of orbit. According to Kepler, all planets moves in elliptical orbit with the sun situated at one of its focus of the ellipse. This is the ellipse. This is the ellipse, and this is semi-major axis A. This is the A distance, semi-major axis, and this is the semi-minor axis. So this is the ellipse, and this is the S, and S dash is the focus. So according to Kepler law of orbit, all planet moves in elliptical orbit, means planet moves on this path, elliptical orbit, and sun is situated on either of the focus. Maybe sun is here or here, and the planet will orbit on the elliptical path. Okay. Second law is laws of area. The line that joins any planet to the sun sweeps equal areas in equal interval of time. Means, let us consider this is the sun and this is the planet, and according to laws of area, the line joining any planet, this is the planet and the sun, this is the line joining, and let us consider it moves from here to here. Okay, so now this will also join, and this will give a particular area. Okay, now consider any other point on the path, this point here. Now consider the same amount of time here. So connecting planet and sun, and again new position connecting this planet and sun. So this area and this area will be equal, and the time here, traveling time of planet from here to here and here to here are equal. Okay, so the line that joins any planet and the sun sweeps equal areas in equal interval of time. Okay, that is, planets moves slower when far from the sun. Here is the sun, here is the planet, position 1, position 2. When planet is here, it will move slowly because it has to cover equal area in equal interval of time. So when planet is far from the sun, then the planet moves slowly, but when planet is near to the sun, it moves faster to cover the higher distance to maintain the areas, equal area. Okay, next, third law, law of periods. The square of time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. So this is the ellipse, this is the sun. Okay, the square of the, so this is the planet P. So time period is, let us consider planet from here. Planet starts moving from here by considering moving on whole path, and when it reaches here, the time taken to move from here by this path and return back to here is time period. Okay, the time period for one revolution of a planet is proportional, square of time period is proportional to the cube of semi major axis of the ellipse traced by the planet. So this is the law. Now question 2, the planet Mercury, this is the planet of Mercury, is revolving in an elliptical orbit around the sun as shown in the figure. This is the sun on the focus, any of the focus, maybe this one is focus, other one is this. So sun is on any of its focus. Now the Mercury is moving in an elliptical orbit around the sun. The kinetic energy of the Mercury will be greater. Where will be the kinetic energy of Mercury will be greater? Since when planet is far away from the sun, it moves slowly, and when planet is nearer to the sun, it moves faster. So V A and VC VB, so VA is greater than VC, because to maintain the equal area in equal interval of time, second law of Kepler. So if V is greater, then kinetic energy is equal to half mv square, that is kinetic energy is proportional to V if m is constant. So kinetic energy of A is greater than kinetic energy at C or any other point, because A is the most nearest point to the sun. So kinetic energy at A is maximum. Okay, that's it. This is the end of this part. Stay tuned, we will continue in the next part. Thank you. So students, we have discussed about the variation in acceleration due to gravity of Earth and what is the reason behind it. We have also discussed about the Kepler's law and its formula. In the next part, we are going to discuss about the application of Kepler's law and around the satellite as well as planets. So stay tuned. Thank you.